In 1985, inside a Rice University lab, a surprising pattern emerged in the data. What looked like an arbitrary arrangement of carbon atoms would soon transform science itself. It was C60, the Buckminsterfullerene, the buckyball.
Dad and I went to dinner, and he told me about this discovery that they'd made, and he was just overflowing with joy because he knew already at that moment that that was the thing. This was the thing that he was going to be known for the rest of his life. And he said, Chad, this is it. This is what people like me, all the people like me who got into science in the late 50s because of Sputnik. This is what we get into it for. This is the big moment.
I remember Rick walking in one day with a piece of paper in his hand that was a mass spectrum, and he said, "Hey, look at this." And it had the peak at the C60 position. He says, "I think we may have really found something here." So that was not exactly people running around jumping up and down, but a real indication that there was excitement about this set of data. It was very shortly after that, of course, that they brilliantly deduced what the structure of this compound had to be, and they were off to the races.
Rick Smalley, Harry Kroto, Bob Curl, and grad students Jim Heath and Sean O'Brien knew that they had discovered something special, but they probably didn't know yet that they had just rewritten the textbooks.
I remember hearing people talking about the third form of carbon, and this was a big deal. Everybody always thought for centuries and centuries that there was just diamond and graphite, and that's all there was.
I knew it was new and different. It was just one interesting molecule at the time. I didn't realize we had revolutionized the whole field of carbon chemistry. That took a few more months, but I was very excited to be working on it, and I was also very excited to be done with carbon and get back to semiconductor clusters, which never happened for me.
I'd come in Monday morning with this data that said C60 really is a chemical phenomenon. It's really worth trying to understand. And then the next morning, when we looked at the geodesic domes, we were looking at Smalley structure, we saw this relationship, and we thought, the most illustrative name for this molecule would be Buckminsterfullerene. I liked it. That was the name. And so I suggested we call it Buckminsterfullerene.
I opened my son's chemistry GCSE book and went to the section on carbon, graphite, diamond, and now the fullerene, C60. So at that point, I realized the reach of Harry's work was so immense that the textbooks had been rewritten. It's obviously opened up a whole new plethora of science. There's a whole division of chemistry, nanotechnology, material science.
If you think about nanotechnology in general, right, the first big discovery in this field has been the C60 discovery, right? That kind of showed people that you can create materials that we have known for a long time, take it to the nanoscale, and you have an entire range of new behavior and properties. I think the discovery of C60, for carbon was almost monumental because a large number of structures at the nanoscale with just carbon showed that you can really engineer things at the nanoscale and make an entirely new set of materials. So C60 was such a discovery. And as you can see, it's been like the poster child for nano for almost 30 years now, maybe more.
But more than launching entirely new fields of research and changing the scientific world the way they did, their impact was personal to their colleagues and families.
Royal Swedish Academy of Sciences has decided to award the 1996 Nobel Prize in Chemistry jointly to Professor Robert F. Curl, Jr., Rice University, Houston, USA. To Professor Sir Harold W. Kroto, University of Sussex, Brighton, United Kingdom. And to Professor Richard E. Smalley, Rice University, Houston, in the USA.
Well, I remember I was getting dressed in the morning, I had the radio on, and they announced the Nobel Prizes on the radio. And it was like, my God, it's Rice. It's Curl, Smalley, and Kroto won the prize. So that was terrifically exciting.
So I had gone to work, and about 8:15 in the morning, he calls me up. I just won the Nobel Prize. What? So I bailed on work and went fogging to the house as fast as I could get there. I got to the house and I said, well, where is he? He's over at Rice. Well, where is he over at Rice? So they're all gathering up in Levitt Hall for a big wing ding. Well, let's go. They videoed Rick in from Yale. So he was on a big TV behind my dad, and all the TV camera people and the print press were all there.
I guess any scientist has imagined to themselves, what would I do if I picked up the phone one morning and there was somebody saying I'd won the Nobel Prize, and no one has ever come up with a satisfactory answer about what I would do or how I would feel. It's great, is all I can say.
I was working at Calvin Klein Incorporated in New York at the time when I said, my dad just won the Nobel. They were just, everybody's face they were just in awe. And it was more of I was so excited because this has been kind of building up for years. Like Dad was saying, I think this might be the year. Oh, it's not this year. I think, well, it's going to be this year. And he had told me a couple months before this, like, I'm pretty sure this is the year they're going to find that's going to happen. And he was right.
Harry never strived for a Nobel Prize.
He always said that anyone who sets out to get a Nobel Prize are doomed to be very disappointed.
Rice's reputation as an outstanding research university went up. A discovery like C60 and then a Nobel Prize, you're going to get a lot of people's attention. And now they're not going to think of Rice as a quality undergraduate institution, which it is, unexcelled by other institutions, which I think it is. But okay, it's a research university. Hadn't thought about that, except of course, scientists know scientists. It gave rise to a much larger awareness of where Rice stood as a major research university, remarkably so because it was so small.
Winning the Nobel Prize for his discovery of C60 really did make a big difference to Sussex's global reputation. Students still talk about his legacy and they're taught about it at Sussex. He had a real mission to take science out from beyond the walls of the lab and the university and engage children, young people, old people with his passion for science.
So what fosters world-class research at a university?
When you were a scientist at Rice, you didn't feel like you were within a very small department with very few colleagues. Instead, you were in a larger community that consisted of people in a number of departments, and like the Rice Quantum Institute. So this pattern of collaboration within departments, between schools, is still very deep at Rice. And that turned out to be a perfect environment for the development of nanotechnology and carbon nanotechnology, which is intrinsically an interdisciplinary field.
The reaching across disciplines is exactly what nanotechnology is. And we had to learn totally different languages because in those days, people didn't have language that crossed disciplines very easily. And so what happened as a result of this is Rice built this building, and they didn't just fill it with chemists. They put physicists in there, they put chemists in there, they put people studying at the chemistry-bio interface. So it was supposed to be a building where different disciplines would come in and be forced to interact because of proximity, and that our students would be talking. So actually, that building, Del Butcher Hall, was the catalyst for all of this interdepartmental, inter-college collaboration.
I think the Nobel Prize, the discovery and the Nobel Prize, raised the standard of research performance at Rice. In part because it allowed Rice to recruit even better researchers, even better faculty, and even better graduate students than it had been doing before, and it was already good.
We published a paper, Ijima-san and myself, and I can actually show you this. This is the first time I think this term carbon nanotube was used. The paper is called The Smallest Carbon Nanotube, where we said that it is possible to have a tubular structure of carbon with a single layer. In 1993, myself and Ijima published another paper. So that was this one. It talks about capillary-induced filling of carbon nanotubes. And this was the first cover with nanotube on the cover of Nature, right? I was playing around with some metals and nanotubes and annealing and stuff like that. And when we were looking in the microscope, we realized that actually some of the metal had entered the nanotube hollow inside. First time again showing that nanotubes can be used as a template to make other materials.
Smalley's having a workshop to discuss making carbon nanotube fibers, and I think I can get you invited. And I said, I made my objection, but what do? You're a young assistant professor, and there is a National Academy member who's telling you to go to a workshop hosted by a Nobel Prize winner, and you go. And it was over a weekend, and they would talk about making these fibers and making liquid crystals, and I would be in the back of the room thinking, I don't care how many prizes and memberships or distinguished academy these guys have. These guys are lunatics. They don't have a solvent, and they're talking about spinning these fibers. Jorge had cut out a paper out of Science and put it under my door. And Philippe Foulin from CNRS in Bordeaux had published a paper making the first macroscopic carbon nanotube fibers. And I read that paper and I understood everything. And so that's when I really, really took notice. I thought, this is not lunacy, is that I had blinders on and I couldn't see how this could be done. And so immediately I went to Georgia and I had ideas coming out of my head very rapidly, and then contacted Rick Smalley. And Rick said, yeah, we just got a grant we're getting a grant from a Navy to work on this, just join us. And that's how I really took notice.
If you could make a cable out of Bucky fibers, even a very thin cable could support objects of tremendous weight.
We made a carbon nanotube swing because we wanted people to be able to interact with it. Why a swing? Well, the ropes that hold a swing have to have two things. One is they have to be strong enough to hold weight, but they also have to be flexible. You don't have that many materials who have both qualities, certainly when it comes out of carbon. I think those two hanging cables are the largest piece of nanoscale carbon fiber that has ever been made. And there's precedent, of course, for using public installations and art to get new materials out to people. For example, for a long time, the largest piece of aluminum ever made was the top of the Washington Monument in D.C. And the light bulb hanging above Smalley's couch is suspended by a carbon nanotube fiber made by Rice spin-off company called Dexmat. This carbon nanotube fiber is strong enough to support the light bulb, but it's also so conductive that it can power electrically the light bulb. Hopefully, as people interact with this exhibit and sit on the couch, they'll have some good ideas. So, as Molly would say, be a scientist, save the world.
The story of carbon didn't end with the nanotube. It unfolded even further into graphene.
It's actually a fantastic discovery because before this, people did not know that a single layer of atoms can exist. People thought this was theoretically impossible, but people actually make this graphene. And after this, people realized, well, you not only can have single layer of carbon atoms, you can have single layer of other types of atoms, and also compounds. So that gives the birth of other 2D materials. You can actually have metals that are single layer of atoms. You can have semiconductors, insulators, and even superconductors. So these are exciting fields and exciting materials to explore.
Rice is a place that first really foster interdisciplinary collaborations. So you can easily reach the boundary of your department and collaborate with chemists, with computer scientists, with engineers, and actually see how you can use your basic science, basic discovery, and apply it to other fields. Also, it is one of the schools that have the best business school in entrepreneurship. And this is crucial because if you want to commercialize and bring your inventions to the marketplace, Rice offers you a huge infrastructure to do so. And I personally started a company also because of that. And third, Rice is really a quantum hub. So it's probably the best institution in atomic physics in Texas, and it's very stimulating to be in such an environment where you can talk to colleagues that are really top-notch scientists in all fields and learn new perspectives and new discoveries.
I definitely think, at Rice, it's we have the Nobel Prize, the medal, the lore is something that all the researchers learn about. We have the ongoing work from the Smalley-Curl Institute, the regular symposiums, the meetings, the collaborations. And many of the folks who overlapped with some of the Nobelists, they're here on campus, they're still doing amazing research, they're sharing their stories and training the next generation of researchers. So it's certainly something that if you are in materials at Rice, or working in that space, which happens across all of these different departments, it's something you're cognizant of and thinking of.
As I look to the future, I truly believe we are entering one of the most exciting times in the history of science. We're witnessing an extraordinary convergence of fields, from quantum materials and photonics to nanotechnology and data science, coming together to completely redefine what's possible. Here at Rice, we're uniquely positioned to lead this transformation. The Smalley-Curl Institute, born from the Nobel-winning legacy of Rick Smalley and Bob Curl, continues to stand at the forefront of nanoscience and quantum engineering. With its three core pillars, nanoscience, quantum science, and material science, the SCI fosters a vibrant and collaborative ecosystem where ideas flow seamlessly from fundamental discovery to real-world impact. For every student and researcher who wants to shape the next generation of technologies, from resilient quantum devices to truly sustainable materials, Rice is the place to be. The same spirit of curiosity, collaboration, and bold thinking that once inspired the discovery of C60 is still alive here today. And honestly, I've never been more excited about what's ahead.